Welcome back. So today we're going to talk about the Isograph compiler. The Isograph compiler is sort of the workhorse of Isograph. It generates a bunch of files that are then used by the runtime, and it's important to understand how it works both now and sort of in the future, at least on a very high level, if you want to have a good time contributing to the Isograph compiler, or to Isograph the project. Okay, so to take a step back, I want to talk about how the Isograph compiler fits into the big picture of things. So the Isograph compiler, what it does is it scans your code base for Isograph literals, so stuff that looks like this. Let's say pet detail route. This is an Isograph literal right here. And it finds these Isograph literals, and then it generates a bunch of files. Then at runtime, there's a Babel transform that finds these Isograph literals and does something with them. So for example, this entry point here, this guy is replaced by something like require dot slash, I don't know, Isograph slash query slash pet by, or pet detail route slash entry point by the Babel transform. And this file right here, let's see. This is one of the files that's generated by the Isograph compiler. So basically, the compiler, it scans your code base, generates a bunch, scans your code base, validates that everything is correct, prints out errors if not, and otherwise generates a bunch of files. So you can run the Isograph compiler in two ways. So first, you can, let me hide this, okay. So first you can run, actually, let me just look at. Whoa, sorry. Let's take a look at this guy. Well, this is how it's run inside of our project. Let me take a look at a different project real quick. Okay, recent. Oh, this guy doesn't exist. Let me see what things exist. Okay. Oh yeah, there we go. Cursor ISO. So when you install Isograph in a directory, in a regular React package, what you're going to install is /isograph /compiler, and then when you run ISO, then when you run yarn, you'll get a yarn ISO command. This guy runs the Isograph compiler once, sort of in batch mode. You can also run it with --watch, and this will basically rerun the compiler on every file change. So this is how you should be watching it. In addition, there is also, I believe, a language server, yarn ISO LSP, that the VS Code server runs underneath the hood. We're probably not going to talk about the language server very much during this call, but that's one of the other options. Okay, so that's how you run it as a user. What actually happens? Let's go back to this guy. Okay, so what happens is that we start in this main file, this main.rs file. This calls start compiler, and this ultimately calls compile and print, which ultimately calls handle compile command. Okay, so this is sort of the main high-level thing that the Isograph compiler does. So the first thing, so by and large, this is sort of the overall plan here. It reads and parses things. So it will read and parse the GraphQL schema. It will read and parse the Isograph literals, and it will combine everything. Hey, Julio. The Isograph compiler will then compile everything into what's called an unvalidated schema. Then it will turn that unvalidated schema into a validated schema. So here schema is being used. It could refer to both the GraphQL schema and sort of the Isograph representation of everything. So I'm going to try to use the word GraphQL schema for GraphQL schemas and then just schema for the Isograph in-memory representation. I will admit this is not the best naming. Okay, then it turns the unvalidated Isograph schema into a validated schema. And if that succeeds, then sort of everything after that is sort of supposed to succeed unless there's something weird going on with the file system. So the next thing we do is we generate an in-memory representation of all the artifacts that we are going to generate. This step should never fail. And if it will fail, it should have been validated beforehand. So we're free to panic at this step right here. And then we delete and recreate the artifacts on disk. Okay, so the reason we do this in two separate steps is so that this delete and recreate the artifacts on disk part is as short as possible and as unlikely as possible to just like run into weird issues due to the fact that we're taking a long time to do this. Okay, so that's sort of the really high level things we do. Then there's a few other things that the Isograph compiler does that are sort of maybe specific to some of the, they're more niche, I guess. First, for example, if a client field is defined on an interface, we also have a step to add that client field to all of the concrete types that implement that interface, and we process the expose as directives. I would consider these like a little bit less core to the overall idea of what Isograph does, so I don't necessarily want to dive into this too much. Okay, let's take before we dive into what Isograph does, like in terms of concretely, let's talk about like how it does it. So right now, Isograph is written, the compiler is written in sort of somewhat of a sequential fashion, in the sense that first we try to parse the GraphQL schema. If we fail to parse the Isograph schema, we'll get an error and we'll show that error to the user. So for example, if we're running let's see, watch pet demo, which is the alias for running Isograph inside of the Isograph, or running the Isograph compiler inside of the pet demo inside of the Isograph repo. Okay, if we do this, one thing we'll do is we can, let's say, go to pet demo GraphQL and I don't know, make some sort of errors. Right, we'll do this, and then, oops, unable to parse schema, and it'll print out all these errors. That's nice. But it also, because of how we did that first, that means that if we, well, let's take this away first, and if we go to, I don't know, pet detail route, and, add some sort of syntax error here, it says, unable to parse Isograph literal, maybe this is not the ideal error message, seeing it now. Okay, we have some sort of failure to parse here, and if we go back here and we add some sort of failure to parse here, well, we don't show the failure to parse the Isograph literal at this point in time. That's like not ideal, because what we really should do is surface to the user all possible errors that we can get, or at least like it is conceivable that what we want to do is to show to the user all the errors that we have encountered. This is especially important when we get to the language server, because if you're writing a Isograph literal and you make a mistake in one spot, well, you don't want all the errors that are visible elsewhere to like disappear. That's kind of a bad experience. And then fixing that one error reveals like 20 other errors. You can sort of have this feeling that like, oh, this will never end. Anyway, we can do better. We can surface all of the errors to the user. Okay, so let's go ahead and get rid of those errors and go back to this. So basically, the way that happens right now is we just call, we use the question mark operator to uh, stop early if we get any errors, and we just do all the steps sequentially. So we should probably find a way to not do that. In the end, the way to not do that, I think, will ultimately be that this sort of thing needs to be essentially a DAG of starting at the root. We need some artifacts. To get those artifacts, we need the validated schema. To get the validated schema, we need the unvalidated schema. To get the unvalidated schema, we need this and the literals. And to get this literal, we need the text. Or I mean, to get this literal, we need the AST. And to get the AST, we need the text, and so on and so forth. And therefore, we can sort of work on this tree as much as possible, and at any point in time, basically evaluate this tree as much as possible. And whenever we encounter errors, well, that's just, we kind of stop, but we can gather all the errors from executing this tree. And this is essentially what the salsa architecture is, which is sort of what they use inside of the relay language, the Rust language server. And that's sort of in the long term, what the direction that I want to take the Isograph compiler in. You said something, Julio. I didn't actually have a chance to read your message.
Yes, I think it's like what Zod makes. When you parse a schema with Zod, it traverses all schema and then outputs an object with all the issues at one time. If it's success or failing, it doesn't matter. If it has one issue or 10 issues, it will output an array of issues with all the data, the path to the issues, and everything.
Nice. Yeah, that sounds like exactly what we want. Okay, so let's take a quick. Oh no, this dot file when I reset things. Oh, it's here. Okay, cool. Awesome. So let me see. Let's go ahead and preview this. So let's talk about what we actually want, which is to say the salsa architecture. So the idea that I have for the ultimate sort of architecture of the Rust compiler is something like this. Right now, the compiler is a batch compiler, so it is, I think, push based. So we're starting from the bottom on the right side, and then we move up, and eventually we get to the artifacts, and we generate the artifacts. Instead, I want this to be a pull-based compiler, and we'll see why. And a pull-based compiler essentially says, we start with, I want the artifacts, which are the generated files. Based on that, I need the validated schema. Based on that, I need the Isograph schema. Based on that, I need this, and so on. And so obviously, this is that data structure that will show us, that will make it easy to surface all of the errors that we have encountered. And secondly, it is also important because it makes it really easy to do incremental recompilation. So right now in watch mode, whenever any file changes, we just blow out the world and start again. And that's not ideal for large projects, obviously. And there's a number of things that we can easily do to reuse parts of the partial results from past compilations. We can, for example, if the schema hasn't changed, just reuse the last parsed schema and stuff like that. Okay, that's great, but it will never get us to sort of the really, really fine-grained incremental compilation that we need in order to get really, really fast and snappy responses. Okay, so, and that's especially important when we are talking about the language server. So with the language server, what we want to do is to be able to respond to changes and not recompile the world whenever the user types a single character. Okay, so take a look at this, right? Let's say we are modifying query.foo right here, right? And the user types some sort of a new space, right? Well, I mean, maybe just make some change. At this point in time, this file has changed. So we say this has changed. Then everything upstream is invalidated. Or everything up to the root is invalidated. So now the AST is invalidated, field query foo, blah, blah, blah. All of these guys are invalidated. And now the next time, okay, let me add something here to this. We want auto completions. I don't know. No, maybe we want some like hover information. Okay, hover information, and that's going to depend on field query.foo, right? Okay. I don't know how to color things. I don't remember how to do that. Okay, so we're going to invalidate everything up until, including the hover information and sort of everything that's up from text of field. Okay. So now VS Code will ask us, oh, I would like the hover information because the user's mouse is like on this character, right? And from there, we go down. So we'll go from hover information, oh, I need this field. Oh, I need this AST. In order to get this AST, I need this text of field. And then it will see that this is different. Then it will recalculate the AST. And then it will recalculate this. And then it will recalculate the hover information. But in this way, we've sort of done the minimal amount of work possible, given that like this has changed. And then maybe later, the user is like, oh, I want to regenerate the artifacts on disk. And maybe we will do that as part of the VS Code extension. I don't really know. But at this point in time, well, we start here and we go all the way down and da-da-da-da-da. And eventually we get to field query.foo. And because we've already hovered, we've recalculated this. So we don't need to do any extra work. We can just reuse the last value of whatever the heck this is. I mean, maybe it's the internal representation. I'm not really sure exactly what it's supposed to refer to in this case, but like something. Okay. The other thing that's needed in this is like, let's say the user just added a space to the text of field, to the text of query.foo. Well, then the AST doesn't change. So we invalidate this, and so on all the way up, right? But then we ask for hover information. So we go out down to here, we check this guy, and then we see that this is modified. So we recalculate the AST, and now the AST is the same from before and after. So because we only added a space. So at this point in time, we know, oh, this hasn't changed. So now we can just reuse the last value of field query.foo, and so we don't actually need to do any additional work. I mean, maybe we need to do some additional work because like the hover information like depends on the space, but like hypothetically the user made a change that didn't actually affect the AST, and so like none of that matters. Okay, so there's some sort of there's essentially two things that we're doing here. One is this tree thing, and then we're invalidating going up, and then sort of recalculating going down, and that is the direction that I want to take the Isograph compiler in the long run. And it's going to be a big project to redo that. I don't see a good way to incrementally adopt that, which is kind of unfortunate. But anyway, that's going to be a big project, and that's going to be ultimately how we want the Isograph compiler to work and be extremely responsive and do the minimal amount of work and so on and so forth. Yeah, okay, I want to stop here. Does that conceptually make sense? Awesome. I'm seeing a nod. That sounds good to me. Okay. So that's all we're going to talk about. That future there. Let's save this one up. Okay. So now let's talk about what we do actually now. Okay. So first, okay, so let's divide this into chunks. So first we call process GraphQL schema extension. We call process exposed fields. Again, that's like specific to Isograph and not like big picture worthy, I think. Then we read project files and extract Isograph literals. Okay, so I'm just gonna make notes here. 1, 2. Then we modify the unvalidated schema with the stuff that we just parsed. This is something that's niche, is add the fields to the subtypes, not super relevant, and add refetch fields, also not super relevant. And then we call validate and construct, so that's the fourth thing we'll talk about. Then we'll talk about getting the artifacts, path, and content, and then maybe we'll talk about writing it to disk. Writing it to disk is what you would expect. Clears out the directory and rewrites a bunch of artifacts. Okay, so let's start with number 1, process GraphQL schema and extensions. So GraphQL has 2 types of files. It has like this schema file here, and then it also has something called a schema extension type of file. Maybe these are technically the same type of file, but anyway. No. They're 2 different things. Anyway, we parse both of them. And in one case, you can modify objects. In the other one, you define objects. That's a very hand-wavy, high-level distinction between the 2. But yeah, just know that GraphQL has both a base schema, and then you are allowed to like add certain things to the schema in other cases. Okay, so inside of here, we'll call process GraphQL schema extensions. We'll do this guy. Well, let me go back to this. We get past the config. Actually, we should probably really quickly talk about the config. The config looks like this. Just a JSON file that matches a particular schema. In particular, has a project root, a path to the schema, a path to some schema extensions, and a bunch of options for sort of grab bag of extra stuff. Okay, so we have deserialized that. We've gotten it, and we've passed it to process GraphQL schema and extensions. Okay, so this guy will read and parse the GraphQL schema, and then read and parse the GraphQL schema extensions, and it will process the GraphQL type system document, which is to say it will add it to the Isograph schema. Okay, so let's talk about parsing. We'll call parse schema parse type system document. Okay, so at this point in time, when we're looking at parse type system document, we have created a peekable lexer, which is just like has divided the input into tokens. And we go ahead and do stuff like we'll parse an optional description, and then we'll parse an identifier. So an identifier would be just any old string, essentially. It's so not a number, not like a symbol, blah, 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 just some sort of string. And depending on the type of string that we get, well, we do something. If it's a type, we'll try to parse the object type definition. If it's anything else, something that we don't expect, well, then we'll throw an error. Not throw an error, we'll emit an error. Okay, so you might take a look at this guy and do like, I don't know, instead of type, do foo or faux, okay? Well, what happens then? Cool, unable to parse schema, expected scalar, found faux. And that happens here because we end up returning this top level schema declaration expected, and this guy has this error error thing here, which comes from this derive error, and it's the error message that we actually show to the user. Okay, let's go back to this. Okay, let me undo that change. Okay, so let's say we're parsing a object type definition. Okay, so here what we're going to do is, again, just going straight forward, from forward to back. We parse the name. We then again parse implements if it's present. Parse constant directives, parse optional fields, and then we return some sort of object that defines what we do. Okay, let's say, what does parsing optional fields look like? Okay, so first thing we do is we check, did we get an open brace? An open, like, that kind of brace? And if we did not, well then, okay, we just don't have any optional fields. Otherwise, we will parse one field, which is at least one field is required by the GraphQL spec. It's a bit, I think, overly complicated in some ways. Like there's no empty sets. Like that's kind of annoying. Okay, so we parse a field and we put it into a vector, and then as long as we don't encounter a close brace, well then we want to parse another field, and then we keep parsing these fields and pushing them onto the vector, and then eventually we get a vector of fields that we then use at the parent. Okay, so what does parse field look like? So parse field will parse a description, which is optional, and then it will get the name, which is the identifier, like the name of the field. It will parse a bunch of arguments, and then it will parse a colon, and it will parse the type annotation. So, it's a string or an array of strings or whatever. It will parse some sort of directives, and then it will return the GraphQL field definition. Okay, so that's pretty straightforward. I think that the schema parsing is actually pretty nice. Like it looks like you are starting from the top. Well, it is. You are starting from the top, and you are just sort of recursively going down and parsing things, and there's almost no situation in which you need to. It's an LL1 parser, so you can always look one token ahead and know what to do. So when we do something like parse optional description, well, we check, is it a single line description or is it a multi-line description? And if not, then like that's fine. Let me see, like open brace, that's what we want to find. Where were we? Okay, yeah. So like optional fields, for example. Well, we just check. Did we have an open brace? If so, then we're parsing a bunch of fields. If not, then okay, no fields. So you never really need to do anything more than look at the next token to know what to do. Okay, so strings and multi-line strings, those are tokens. So, yeah. So you're only looking at one token ahead, even though sometimes like the tokens are somewhat more complicated. Okay. At least I think that's how strings work. I'm not going to check right now. Okay, so there's probably not a lot of work that needs to happen inside of this because GraphQL spec is like, it is a spec. It's slow moving. I don't expect us to deviate from the spec with respect to the schema. So this code may be more or less done. However, it can be improved. So for example, if we, fail to parse query here and then fail to, and then have something else broken here, right? Well, this guy, whatever is doing the syntax highlighting here, understands that type mutation and interface node, et cetera, are done correctly, but we don't, and we only show the first error. We show the error on foo query, but not the error on foo viewer, right? So we probably could figure out how to recover from errors and omit more errors in this case. And I think the way we can do that is essentially, we know that these curly braces are always matched, so at least we can always retry whenever the curly braces go to 0 and maybe show at least one error per top level type. I don't know, maybe. That might be an improvement here. Okay. The next thing I want to talk about with respect to parsing the schema is specifically what we get back. So we get back this GraphQL type system document. Okay, so this is a vector of something called a with location of a GraphQL type system definition. So a with location is a wrapper around a location and an item. And a location here is either generated or something that's embedded in some sort of text. And basically, this location is used, actually, let's take a look at embedded location. Embedded location takes a text source, which is just a reference to a path and a location in that path, and then a span within that text source. Let me see what... Yeah, I guess the span is optional. If the span is missing, then it's the entire text source. Okay, so this guy, this embedded location, is what we use to print out sort of the error message. Okay. So, yeah, this guy gets an error message. This guy is wrapped in a location. Object type definition here will have spans usually. It's not like super well thought out, so there's like a bit of confusion between locations and spans in the code. Sometimes we'll only pass the span and then just assume that the location is the same as the parent, which is not ideal because, for example, this oh yeah, so fields here, for example, they have their own location. And the reason they have their own location rather than a span is because inside of a schema extension, which has a different location because it's a different file, you can add additional fields. I don't know if that makes sense in Isograph, but like you can do that. So if we were to just use a span there and the location of the overall type definition, which is where it was defined originally, well, we would be printing the wrong error location. So some things have locations, some things have just spans, like this description is a span, probably because that's how it was originally, and the description cannot be added in a schema extension. So that's sort of okay, but maybe everything should be locations. I don't know. Probably locations are really cheap. There's like a few bytes, and it's not really a big deal to throw a bunch of them around. That's my thinking. Okay. Yeah. Okay. The next thing is that these fields, one thing you can do inside of a schema is, well, okay. So when we're parsing this first, we don't know whether the type pet will ever be defined. We have to accept this because the pet could be defined below. But if we have something like pet foo, right? Well, then eventually we will throw an error. But not when parsing the schema, like unable to parse schema, right? And now we have a different message, error when validating the schema. So initially, the types that the user refers, the types that we generate are strings, essentially, rather than identifiers, rather than indices. Okay, so inside of here, when we go to fields, GraphQL field definition, type, we'll have a GraphQL type annotation, which is a wrapper around an unvalidated type name. An unvalidated type name is essentially just a string that we have not validated. And this guy is some so-called string key new type. We're going to see a lot of these later, but these are essentially wrappers around interned strings. And yeah, we'll talk more about them later. But the point is, like, in the Isograph compiler, we use a lot of strings, and it's really important that we don't mix up the types of strings. If you are able to pass an object name where a field name is expected, well, you're just setting yourself up for random errors that are hard to understand, that will occur at runtime, and so on and so forth. So we have a whole bunch of new types, which are just zero-cost wrappers that exist only on the type level, around a bunch of different types of strings. So all of these guys, all of the GraphQL type names, scalar type names, et cetera, are their own new types, so we can't like accidentally mix them up. Inside of the Isograph world, there's Isograph type names. Aliases are their own new types, names, and then and then we have this ability to convert with zero cost from certain types to other types. So for example, you can always convert a name, a scalar field name, to a selectable field name, because sometimes we want a selectable field, which is like either a scalar field or a linked field. And okay, a selectable field name makes sense there. And then also field name or alias is similar, which is that sometimes you want either a scalar field name or alias, or a linked field name or alias. And this is sort of like the more generic type. I guess you can think of this as like a union. Like this is the union and this is the concrete. This is the specific type in the union. Okay. Why would we intern strings? Let's talk about that for a second. Well, we use a lot of strings in the Isograph compiler, strings are expensive. Instead, what we do is we essentially put them in a hash map or something like that and return some sort of index. And therefore, we could just pass around this U32 everywhere, which is cheap and free to copy, and I mean, easy to copy, and so on and so forth. And we don't really have to worry about, okay, we're comparing strings, we just have to compare indices, and so on and so forth. So this is cheap. Every single time we encounter a string, we just intern it. And we try not to do that too often, right? But like when we're parsing the schema, we need to do a lot of interning. And from then on, all of the data structures will just contain intern strings. Okay. That is what I wanted to talk about with respect to the GraphQL schema. Okay, so we call parse schema. And then we will get that back. We'll do the same thing with the schema extensions. Okay, I mean, it's pretty similar to what happened before, not particularly interesting. And then we'll call process type system document. This guy will take a unvalidated schema and it will add it to the schema. The only thing that we do here is we do a little bit of validation, which I don't really like. For example, if we have already defined a particular object, well, we're going to throw an error. You're not allowed to redefine something twice. Again, I don't like this because it's a one error that we encounter early on rather than later on, rather than surfacing all the errors later on. And yeah, so we do a little bit of validation here. Okay, so let me talk about what the schema is. The Isograph schema, sort of the in-memory representation is. So we can talk about, let's see, other. So Isograph schema. Okay, so inside of here, okay, so this is the schema. The schema contains a vector of server fields and a vector of client fields, and server field data. These are the three important fields here. Three important things here. Yeah, go for it, Julio.
Yes, I was thinking about the errors handling. Maybe if you put as a result with OK and error. On OK branch, you process as you are doing, but in the error branch, you just add the message error and the data of the error in a kind of queue or stack, and just don't continue the process of this current node, but go on with the process until the end of the tree. So you can have a big picture of all issues without processing unnecessary fields.
Yes, we actually do that in some cases. It's just like it's somewhat ad hoc and it is coarse grained. So for example, if we have like pet by name, right? I don't know, just make something that doesn't exist. Well, we'll print that out, right? And then, okay, let me schema. Let me fix this guy real quick. Okay, pet. Okay, we see that we have an error here in pet by name, and then also if we have pet detail route and we, like break something here. Oh, are you both seeing my? You're not seeing my desktop?
I'm just seeing you.
This entire time I've been not sharing my desktop.
No.
Just a couple of minutes.
When I started talking.
Okay, cool. Let me go back to sharing my desktop. That's odd. Okay. Okay. Let me know if that ever drops off again. Okay.
It is still off.
Yeah. Okay. What was the last thing you all saw?
We saw nothing.
Okay. Did you see the schema? You saw this
No,
file.
Yep.
Yeah. Okay. Cool.
after,
Okay.
yes,
Yeah. Okay.
yes.
Okay. Okay. Then it was really really short. That's good. Okay. Okay. So we do that, for example, when validating. We validate each thing individually or sort of in isolation. So for example, if we have an error in the pet by name and pet detail route, well, then what we're going to see is 2 errors printed to the console. However, we can have multiple errors. Well, in this case, we only have 3 errors because the pet detail route inner doesn't validate all of the fields independently, but we do validate the entry point. I mean, sort of the overall fields independently. So yes, we do that just like in very specific cases, and it is ad hoc, and it's not ideal, I think, how we're doing it. But yes, that's a good call out. Okay, so the important things to note on a schema are that we have a vector of server fields, a vector of client fields, and a server field data struct. And a server field data struct has a vector of objects, scalars, and a hash map of defined types, which is from the name to a selectable server field ID, which is a enum of either an object or a server scalar. So this is... Yeah, okay. So when we process that object type definition, what we're going to do is we are going to okay. Yeah, essentially we're going to call objects.push. We're going to push a new object onto the vector of objects there. And this guy will contain its own set of encountered fields. Let me take a look at that real quick. So inside of schema object, inside of the schema object definition thing, we have an ID and we have a set of encountered fields, which are themselves an enum that's either it's a server field or a client field. Okay, so when we go back to this, okay, so what are we doing here? We're pushing a new object onto the schema, and then for each of the fields, we're adding a bunch more fields on there, and then we are, what is this vacant object here? This is encountered root kind. Why do we know that this is a root? That seems weird. Okay. Well, anyway, we push the schema object onto the vector of schemas, and then we extend the fields. So essentially we have some vectors where the names of the... we have some vectors containing a bunch of objects and a vector containing a bunch of fields, and we push onto those as we have gone. Okay, so remember what I said earlier is that we don't know whether the types exist. So this unvalidated schema fields object here has this type, is a vec of unvalidated schema server field. So a schema server field here is what we have generated. And what this guy has is an associated data type. This thing originally, or an associated data field. When we initially construct stuff, the associated data will essentially be the untyped string, the unvalidated string name. So this will be pet foo or something like that. And this schema server field is generic over the type of this guy. What is this guy? Oh, also it's generic over the type of the arguments. But like most importantly, it's generic over the type of the data. And initially in the unvalidated schema, that type will be unvalidated, will be some sort of unvalidated thing. So if we take a look at this schema right here, so these are the generic types here. associated with the schema. Don't really worry about reading all of them. But the point is that server field type associated data is a GraphQL type annotation of an unvalidated type name. Okay, we haven't done any validation that the type actually exists at this stage. That's going to become relevant when we start to validate things. Okay. Yeah, okay, so we create a bunch of objects, we push them onto a vector, we know the IDs, so when we, because the ID is just the length of the vector at this point in time, because we're just creating new ones, so we can always create the IDs, and we always have a schema that is, where you can get an ID, which is not actually a pointer, but is just an index. And then whenever we look something up with that index, we just panic if it's not there. And we sort of have to do a little bit of work to maintain that guarantee. But not a lot of work. Just at construction time, like make sure you're creating a valid ID. Nothing is ever deleted from the schema, so it's really easy to maintain that guarantee. Okay. Let's go back to what we did when we processed the stuff. Okay, I don't know, process type definition. Yeah. Okay, process type definition. Okay, let's find this guy. Yeah, okay. So we did that, and we got and then we did the same thing for the extension documents, and now we go back to handle compile command. Okay, so what have we done now? We've processed the schema, we've parsed the schema, and we've added it to the unvalidated, added those types and fields to the unvalidated schema. Okay, then next thing we do is we read project files and extract isoliterals. Okay, let's take a look at what happens there. We read all the files in the folder, and we call extract isoliterals. Extract isoliterals here essentially uses a big old fancy regex yep. Just uses this regex to look for isograph literals. And if we get that, then what we're going to do is we're going to create this isoliteral extraction object that contains the stuff that we extracted. Okay. Okay. Let's see, call batch compile. Okay. So, and then what we do is we process the isoliteral extraction. So this guy will attempt to parse the isograph literal. Okay. Parsing the isograph literal. Very similar to parsing the GraphQL schema in the sense that it is LL1, so you only need one token you only ever need to look ahead one token, and so on and so forth. So for example, here we'll check what's the first thing. I guess we'll call it a discriminator here. So entry point or field. We're going to add stuff like a pointer, right? Like this is something we're going to do eventually. And so on and so forth. Like if there's new top level things, they need to be added here. Okay, so let's take a look at an entry point declaration. So for example, an entry point, oopsies, what did I just do? An entry point looks like pet detail route. Something like this. It's the keyword entry point, the name of the field, dot, and then the field name. Okay, so you may be already able to guess what happens in the parse isograph declaration thing. We parse an identifier, the name of the field. We parse the dot. We parse the client field name. And then we return an object. Okay, so it's nice. It's straightforward. Not a lot we can improve on here, except for maybe like make this a little bit less busy. Like there's a lot going on here for not a lot of actual work, but it's conceptually pretty simple. And then the last thing we do is we check, is there anything left over? In which case, oh, that's a problem. Okay. Yeah. Okay, let's go back to this. Isograph field declaration, also similar. Does stuff like parses the identifier, parses a period, parses an identifier for the name, and parses variable definition, directives, and descriptions, and so on and so forth. There's a lot of room for, I think, innovation inside of the syntax and I think it would be really cool for us to add other things here. Like I have a lot of ideas for what should be supported in the syntax, or like how to make the syntax work better. And yeah, that's a thing that there will be a lot of cool additions here, I think. Anyway, okay. Parse the isograph literal here. Again, when we initially parse the isograph literal, we don't know whether all the fields exist. So the item that we get back is generic over a type, and it contains unvalidated type names. Okay, so where were we? Inside of batch compile, we called parse iso literal, and then this guy, and then we push it onto some stuff, and blah da da da. We call this, and then we call validated isograph field directives. Okay, so we're just checking like a few minor things. That's not super relevant to this case. Oopsies, and then we go back here. Okay. Next thing we do is we add the client fields to the schema and add the entry points to the schema. Okay, so add client fields to the schema. Really similar to adding the object types to the schema. We will find the object, make sure it exists, and add it to the object's encountered fields hash map, and then also add it to the schema's client fields array. Okay, so when we add it to the encountered fields hash map, well, the value is sort of this thing. It contains a client field ID, and the client field ID is just the length of the client fields, and then later we push it on and we give it that same ID. Okay. So, yeah, okay. Some of this stuff is, yeah, okay, that's essentially what we're doing. We're pushing it onto some vector of client fields, and we're adding it to the object. So essentially, the object knows about all the client fields that it has, and the schema has a vector of all the client fields that have been defined. And yeah, okay. So this client field here is generic, again, over a bunch of types. One of the types is associated data. And initially when we create this, that associated data is the unvalidated type name. Okay. So let's go back here. Okay, so we've added the client fields to the schema, added the entry points to the schema. That's also pretty simple. And then next big step is validating and constructing the schema. Okay, so the schema here is generic over 5 types that are encapsulated in this trait here, right? So these 5 types. The unvalidated schema contains one set of values for these types, or one set of types for these associated types, and the validated schema contains a different set of types for this thing. So essentially what we're doing is a giant dot map that changes the type of the schema. Well, or an and then that changes the type of the schema and exposes a bunch of errors, or surfaces a bunch of errors. So what are we doing inside of batch compile? We call validate construct. So we're given an unvalidated schema, and we return a result of a validated schema. Okay, so this is where we do what Julio had suggested, which is keep a vector of errors. And then what we do is let's take a look at how we validate the entry point. Okay, so we start with an unvalidated entry point, again containing a unvalidated type name. And what we want to do is ensure that the type exists, the parent type exists, and the field name exists. I suppose when we first create the entry point, we could validate whether the parent type exists. We probably don't want to do that. We probably want to defer that as much as possible. So hopefully we're only doing it now. I'm not really sure. Okay. Let's see what entry point type and field is. Yeah, cool. It contains a bunch of unvalidated type name and scalar field name and stuff like that. So just kind of unvalidated stuff. And we will go ahead and call validate parent object ID. This guy will look at the server field data thing, look at the defined types, and pass in the name. And if we don't have it, then we return an error. But otherwise, we get a selectable server field ID, and we ensure that the server field ID is an object. And otherwise, if it's a scalar, like if you try to define string dot some client field, that won't work. We throw an error. Well, we emit an error here. And here, what we do is we I don't know what this is. That seems kind of sus. It's probably some stuff that we need to refactor and clean up. But otherwise, we just return the object ID. Okay. Yeah. So basically, what we've done here is we've checked that this type has been defined. And if not, well, let's see. If it's a scalar, we're going to return this invalid parent type. And if it's not, then we're going to return parent type not defined. So if we go to pet detail route, I don't know, let's say string, right? This will tell us string is a scalar, right? Okay, cool. That's what we expect. And query foo is a type that has not been defined. Awesome. So kind of what we expect. Okay. And then same thing with the client field. We just ensure that it exists and it is a client field. And we essentially return a... Okay, so now we have this updated entry points vector or hash set. Okay, and this updated entry points hash set ends up going into the validated schema. Okay, so we started out with a schema containing a vector of entry points or whatever that are unvalidated. We validated them, and they end up in the validated schema. Okay, hopefully that kind of sort of makes sense. Even though there's a lot going on in here that sort of like makes this hard to just read. Okay, so the next thing we do is for the schema. Let's do the same exact stuff with validate and transform server fields. We will do exactly the same stuff. Validate that the server field exists. So this is the... Okay, so we have a server field type. So we have like a field which is like... right, we have this guy, pet foo, right? It's just some unvalidated string. We call .inner. Okay, let me just close all these other ones. They're very distracting. Yeah, we call .inner. This will give us like that pet foo unvalidated string. We're going to try to get it in the schema data.define types, that hash map of string to what is it. And if we don't find it, well, then we're going to emit a field type name does not exist. And lo and behold, that's what happens here. We find that this field type does not exist. Okay, so we go back to doing this. Okay. Then we validate some sort of arguments, and now we have a schema server field, which is validated and has the correct type. And otherwise, we sort of return some errors. Okay. And then so whenever we're validating an array of items, it's actually pretty easy for us to return all of the errors, as long as they're sort of independent. So we have this get all errors or all okay iter function, which returns all of the errors, well, runs some sort of function that can fail, and then collects all the errors and returns those if anything has failed. And otherwise it returns an iterator of all the validated stuff. Oh no, a vector of all the validated stuff. Oopsies. Okay. So now we go back here. All right, we also do the same thing for validating and transforming client fields. Let's see what happens. Validate the variable definitions. We validate that the selection set exists and works. Yeah, okay, I mean, it's more complicated, but it roughly does the same thing. Takes something containing a bunch of strings and returns something containing a bunch of IDs. At every point in time, every single string has to be looked up and confirmed. And then we have to make sure that, if you're selecting a field like query pet, right, that there actually is a field called pet on query. And if you're selecting pet with a curly, like pet is not a scalar, and blah, blah, blah. Like all this kind of stuff we do in this situation. Okay. I don't want to go into that because that's just a lot of details. Okay. And then we return the validated schema. And at this point in time, we have done everything, and nothing should fail except for writing to the file system. Okay, so if we go back to batch compile, we have made it through validate and construct. Okay, the next thing we can do is call get artifact path and content. This is another big thing. This is something that should never fail and returns essentially an array of like, we're generating this file and it has this contents, or a vector of that. Okay. So here what we do, so here's the overall strategy. We try to generate only the files that are actually needed. Is that super necessary? Maybe not, but it still is kind of nice to not generate unneeded files, I think. Okay, so essentially what we do is this. We know that every single client field needs to be in the iso.ts file, and the iso.ts file will refer to its param type. So every client field needs a param type, and the iso.ts file needs to be generated. Then, for every entry point, we need to generate an entry point file. That includes the query text and so on and so forth. And this entry point requires a reader AST for that one, and for all the things that are referenced recursively as part of that entry point. So essentially we're building up some sort of queue of artifacts that we need to generate as we go through the entry point. Okay, so for each entry point, we generate the entry point artifacts, and we have this global client field map, which is where we accumulate all of the client fields that we have encountered, meaning that we actually need to generate some sort of artifact for them. Encountered outer types. Oh, yeah. I don't know why that's two separate things. I would have thought that this was the same thing, but maybe it's not. We'll see. Okay. And then for every single client field that we have encountered in this global client field map, we note several things. For one is like, did we ever select this field loadably? If it's selected loadably, well, it needs to be its own entry point. And okay, and then what we do is we generate some stuff that depends on like sort of the type of the field that we generated. It might be an eager reader artifact. It might be a refetch reader artifact, and it might be this really could be simplified. It's a lot of stuff that could be moved elsewhere. Could be an imperatively loaded field, in which case we generate a refetch reader artifact. It's kind of a lot of complicated stuff, but like the most basic case is that we generate an eager reader artifact. So if this is a user written artifact, such as like pet detail route or whatever, then we generate an eager reader artifact, and this guy generates a reader AST, and then generates a bunch of stuff that we put. We generate a reader AST. Let me find that reader AST again. And this guy, that's like a stringified reader AST, and then we put it in here. But yeah, we generate an artifact based on this. Okay, this is a little bit like we're just concatenating a bunch of strings. Certainly something that can be improved about this is that we actually use something like actually create some sort of data structure that ensures that it is valid JavaScript, because it's really easy to have bad formatting and have invalid JavaScript and something so on and so forth. So eventually, I think it'd be good to use some sort of like actual JavaScript or TypeScript AST library and generate all of these in that way. And that's probably going to be a lot easier to do stuff like reuse code across these generators. Okay, but we generate this, and one of the things that we do here when generating these guys is we have these imports, function import statement and reader import statement. So if we take a look at resolver reader, I don't know, pet check-ins card, that's a good one. Well, we are importing, this guy. Let's say this guy, this resolver reader statement, I believe, reader import statement. Anything that's referenced has to be imported, right? So this guy is used here. So this check-in display is a field that is referenced inside of pet check-ins card. Yeah, check-in display. That is a client field. Okay, so because we reference it, it has to show up in the reader AST, and therefore it has to be imported. So inside of here, this reader import statement, when we generate the reader AST, we both traverse the field and create the string representation of the reader AST, but also say, hey, when we are encountering any resolvers, well, we need to put them in this reader imports B tree set. Okay, why are we using a B tree set? Okay, we could use a vector of imports, right? But then if you use the same client field twice, we're going to have the same import twice, and therefore the generated JavaScript is not going to be valid. So what we actually need is a hash set. Okay, well, if you have a hash set, what happens? Well, you make one random change and then suddenly ordering changes. So a B tree set is a hash set with a defined order. So we're creating a B tree set because for anything that gets outputted to a generate artifact, we need to use B tree sets or B tree maps. Yeah, I think that's what they're called. In order to have a guaranteed ordering of the files so that some random change doesn't cause like imports to get reordered in unrelated files, and like that's just stressful for users. They don't understand why it's changing, and maybe as they run recompile, it like generates stuff in a random order. That would also be bad. Okay, so generate a bunch of reader imports, and then we iterate over each of those and generate the import statement. Okay, pretty simple. Maybe not the prettiest code in the world, but at least it works. Okay, that's how we generate reader artifacts. Let me take a look at this reader artifact and just see if there's anything else. There's not anything else that I particularly care to. Yeah, okay. That's how we generate reader imports. Reader artifacts, okay. Okay. Okay, and then for every user written client field, we also need to generate a param type. So remember, this is what I talked about. The iso.ts file needs to contain the param type, because iso.ts here imports all the param types. And then if you write an iso literal that starts with field add item display, well, it is this thing, and that references that param type. And then that's how you know that add item here has this exact type. And also parameters. It will tell you that this is, it'll give you a type for that. Okay. So, am I on the latest master? I might not be on the latest master. Yeah, I'm not. Okay. Yeah, there we go. I knew that because the type of parameters is now different. So this is something that Vadim just landed that I'm super, super excited about and have been gushing over for days. Okay. So for every user-defined client field, we have to generate the eager reader param type artifact, and then we extend it to the encountered we add it to the encountered output types, and then for each we generate a reader output type artifact. What is that? Oh yeah, okay. So whenever a type is referenced in another, a resolver references another type. So a client field, if it references another type. So for example, the pet check-ins card selects the check-in display. Well, we need to know what type of value we're going to pass to pet check-ins card at that pet check-ins display location. And the way that happens is we create this output type. So this guy, so for example, if we're at pet check-ins card, actually let's do pet check-ins card resolver reader, right? Actually, no, let's do param type. That's what I want. This guy, this is the value that we pass as part of that first parameter to pet check-ins card. Well, the pet check-ins display, what type does it have? We don't really know by default, and that's like a shared thing because pet check-in display is going to be used in a bunch of, check-in display could be used by a bunch of client fields. So here we use the output type, and that output type is this thing, and it's just whatever we happen to generate. So every time we encounter a client field, and we are generating the param type, well, then we also need to generate the output type for all of the fields that we reference. So if that param type, if that client field is not a user-defined type, for example, it's like a refetch field. Refetch fields are automatically generated. Well, it has an output type, but it doesn't have a param type. Okay. Yeah. Something could have a param type, but not an output type also, if it is just a client field that exists, but is not selected anywhere. Maybe it's kind of a useless client field right now. It's really hard to use it because you have to actually select it somewhere. But like at that point in time, it will have a param type, but if it's not used anywhere else, it will not have an output type generated. At least that's what's supposed to happen. Okay, so we go back here, we generate the output types, and then we push it onto this thing, and then we build the ISO overload, which is that iso.ts file, and we return the path and contents. Okay. And then we go to batch compile, and we call write artifacts to disk. That removes everything from the directory, creates everything, and keeps track of the count? Why do we not just return oh, it's an into iterator. That's why. Okay. Okay. Okay, whatever. And then we create these files, and then we return, and then what happens is we get a count, and we create these compilation stats, and we print that out to here saying successfully compiled 31 client fields, 8 entry points, 140 artifacts, and 122 milliseconds. That's how the compiler works. Okay. Now might be a good time for me to stop and just like answer any questions.
Yeah, I have one question.
Let's do it.
Where is the event when we start compilation in watch mode? So we just observe root directory, right?
Yeah. So let me dive into that. So if we go to main.rs, we have handle watch command. This guy creates a watcher, which is something that where is
just
create debounce file watcher? New debouncer. Debounced watcher. New debouncer. What is this? Notify debouncer. I mean, it uses some sort of library. Honestly, I thought it might be Watchman.
Yeah, that was my question. Relay uses Watchman, so do we need to use it?
I think we use Watchman, yes.
Do you think?
Okay. But I think it is also something that, like, we don't know that we use Watchman per se. It's some sort of library that provides a shim that is generic across, like, it works on iOS, works on Windows, and maybe it has a different implementation in the different platforms. So we watch the project root, and we watch the schema file, and we watch the schema extensions. And then what we do is whenever we receive an event that something has changed, we check if it's inside of the artifact directory, so we don't create like infinite loops, and then we call compile and print. So
eventually we know what exact file has been changed, right?
Yes, exactly. So maybe we have an issue here, which is like if we have pet detail route, let me create some spaces here, and then pet summary card, I don't know, create some extra lines, and we save everything. We're going to get maybe 2 events. Oh, we only get 1 event. Oh, that's kind of nice. Okay, we only get 1 event that multiple files have changed. So we don't recompile twice. Oh yeah, any modified path is outside of the artifact directory. That's kind of cool. It gives us a vector of debounced events. And maybe the reason it does that is because it's like actually debouncing. So even if they're like 10 milliseconds apart, like it adds some sort of like 50 millisecond delay or something. Yeah. Yeah. So I know that's a lot and it was kind of a very high level, very fast, but hopefully that'll make it easier to sort of understand where to look to make certain changes. And what kind of stuff we want to sort of implement sort of in the long term inside of this. Yeah, I think the biggest one here is like the biggest 2 are the incremental compilation mode that we talked about early on, like that salsa architecture, and then supporting new features, so like adding stuff, adding validations, adding stuff to the syntax, and so on and so forth. And then I'm sure there's a lot of stuff that can be made more efficient about this, but like incremental compilation is, I think, the big way that we're going to make this more efficient. So I'm not like super concerned about performance at the moment, but yeah. Actually, there's a few other things that we can talk about real quick. When we generate the artifacts, like I just sort of like breezed over, we generate the entry point, which includes the query text and so on and so forth. One of the things that we do, this is just like a random aside, is we generate the query, right? Actually, let me find one with a pet detail route. This has like it auto aliases everything. So check-in, skip, L, null, limit, blah blah blah, or pet ID VID, right? This is like a way of encoding, like we are using the variable named ID and stuff like that. It would be better, because this actually gets sent back to the user, to instead just have like a bunch of number, or like just like, you know, some sort of aliases like this, or maybe letters, I don't know. Yeah, stuff like this, and then presumably that would create a much smaller network payload. I'm sure in most cases everything is gzipped, so it's like debatable whether this would be better, but it could potentially be better because this can be really long, and like doesn't seem ideal to do that. That's one thing that we can do differently. The query text obviously we need to support persisted documents or trusted documents, I guess they're called now. So instead of like actually including the query text here, another thing that will be big is, well, right now, every entry point contains the normalization AST as a hard require. The normalization AST is used for two things. One, I mean, most importantly, it's used to check is to write the network response into the store. And so if this was, something like this, import blah, 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 right? Then we could load the normalization AST only when we kick off the network request. And like, we don't want to do that for every case. Like on pet detail route, you're kicking off the network request right off the bat. So maybe you want to have the normalization AST immediately ready. But in other cases, like if you're kicking off a network request when the user hovers over a button or clicks on something or whatever, then not having the normalization AST immediately is super helpful. So this will be something that spans both the compiler and the runtime side, which is to have normalization ASTs that are asynchronously loadable only when you kick off a network request. The other thing the normalization AST is used for, well, there's several things, but like one of the other things is checking whether we have enough data in the store to serve the to not go to network. So obviously, we need the normalization AST if we want to potentially avoid going to network. Or we need to fetch it first. I don't know, one of those two. And so I think the ultimate thing is that we need to basically have two types of entry points. One is like either this needs to be like encoded in the type system. And if you want to use an entry point with, and potentially avoid going to network, then the normalization AST needs to be a hard require. And if you are okay with always making the network request first, well, then the normalization AST can be loaded lazily. Or I guess there's a third option, which is like load the normalization AST first and then check whether you need to go to network. And that's probably fine in actually most cases, because normalization AST is like some static JavaScript, and that'll download really fast. It could be really big though. So that's one thing. I think also okay. That's one example of something that one example of some of the work that we would do here. I think that's actually a pretty big one, a pretty big win, and it is something that, especially for stuff like mutations and subscriptions, like you don't need the normalization AST during the initial payload. It's just a waste. And the normalization AST contains, it like is O of the size of the entire query rather than of just the outer fragment, right? So it could be really, really big. That's some of the stuff. Okay. Anything else I can, opine on? Well, sweet. Thank you all for coming, and I hope the folks that are watching on YouTube are, I hope you got something out of this. Sweet.